we couldn't get GGU or upgrade to agree for any extra classes. Two reasons are cited. One was that we don't have any room to play at the end of the course, so extension beyond the prescribed final date is not possible. That's one reason. And the second reason, we were thinking about having an extra session during the weekdays, and even that was rejected because they were worried that some during the weekdays, few may be able to attend, few may not be able to attend, and hence they said that that's also not possible. So I was told categorically that I better finish on time or on the schedule, complete all the topics on the within the scheduled dates. The only room I was given to play was I could extend the sessions beyond the 2 hours 45 minutes limit, which I think I will have to do, because otherwise we might not be able to do much. My memory is today is the 10th session. I think today is the 10th session. And after this, I have only 3 sessions. There are too many lab sessions. I'm not sure. I hope those lab sessions are useful, but I get a feeling that we will have to rush in the next 4 sessions starting today. Okay, so with that said, what I am going to do is I'm going to turn on the complete lecture mode. Of course, I don't want to kind of completely turn off the discussion mode. Okay, so we'll have some discussions, but let's try to cover as much ground as possible in the next 4 sessions starting today. Okay, so in the last session, and that's why usually I wait for about 5 minutes for the quorum to be reasonable, but today we have only about 15 or 16 people now, so people might be slowly joining in. So I'm not going to wait for them, just start the session and continue from where we left off last weekend. Okay, so last weekend, the last session, we studied about multiple linear regression, and we covered 2 very important ideas in multiple linear regression, namely, how do we deal with right? We dealt with categorical variables, and then we also dealt with interactions. 2 very important challenges when we deal with multiple linear regression, that is when you have more than one independent variable in the problem. Now, the most important, actually we covered all the 3. The most important challenge is the true independence of these independent variables, right? Even though we call them independent variables, it is not clear whether they are truly independent of each other or not. Therefore, we decided we will come up with a test to check that. And what we did was we came up with this idea called variance inflation factor. This is a method by which we check for every independent variable whether it is multicollinear with the other variables. That is, whether that variable can be expressed as a linear regression of the other variables. And how do we do that? For each of these models, for each of these variables, we build these models, and for each of these models, we have R squared, and a nonlinear function of the R squared is the VIF. VIF is equal to 1 over 1 minus R squared. So when R squared is 0, VIF is 1. No, that is very poor or no correction of the total errors. Okay, that means it is not a good model. That means this variable is not dependent upon any other variable, right? But when R squared is 1, then the denominator is 0, therefore VIF blows up, goes to infinity. Therefore, we set some value intermediate, VIF as 4. Why 4? When you set R squared is equal to 0.75, then the denominator becomes 0.25. Therefore, VAF becomes 4. So R squared is 75%. That is about 75% of the total errors. If it is corrected, then we say that there is a strong relationship. That means that variable, which has an R squared value of 0.75 or greater, is said to be multicollinear with other variables. R squared is equal to 0.75 means VAF of 4. So VAF of 4 is usually considered as the threshold for determining whether a particular variable is dependent upon or multicollinear with other variables. Okay. Now, if we are very lenient, okay, that means we want very strong evidence of dependence. That means R squared value should be very high, right? So when the R squared value is very high, that means we are looking for a very strong relationship. That means we are very lenient about this multicollinearity. Okay, that's what it means. So it's a counterintuitive argument. Okay, even if the dependence is fairly strong, let's say 0.8 or 0.75 R squared value, I'm going to still consider this variable to be independent of others. That means we are very lax about this interrelationships. That's what it means, right? So as the R squared becomes large, or as VAF becomes large, that means we are very lax in our criterion for independence. But if we set VAF to be smaller number, let's say we set VAF to be 0.5, sorry, R squared to be 0.5, that means VAF to be 2. That means even if the R squared value is 0.5, we say that it's a strong relationship, therefore there is multicollinearity, therefore this variable has to be dropped off. That means we are very stringent. Okay, so as VAF increases, that means we are very lax in our independence condition. That's what it means. Okay, so with this VAF, I think you could play with these examples, but then many a time what happens is when there is a large number of not necessarily a large number of variables, but many a times it might not be meaningful, or it might not give us a very clear idea of how to go about proceeding to check VIF or any other methods. Okay, and in these situations, what people do is people go to a classic technique called multi-stage model building exercise. Okay, so I'll describe what that means using this particular example. What we are going to talk about is what is called a stepwise regression. Okay, stepwise regression. So we are going to go step by step. To do that, let's start with an example. Okay, here is an example of world oil output. Okay, whatever units. Okay, this might be in millions of barrels per day. Okay, few years ago, and since US is the major consumer of energy, so we wanted to see whether world oil output can be modeled just based on the US energy indicators, energy consumption indicators. Say, for example, how much energy overall the US households use in some unit, British thermal, millions of British thermal units, I think, US auto fuel rate, US nuclear production rate, US coal production rate, and US dry gas in whatever units, some different units. Let's not worry about the units. But these 5 variables related to the US energy production and consumption, we want to see whether we can use this to model the world crude oil output. Okay, and here is some sample data for that. Okay. Now, how can we go about doing this? Very simple. You could build a multiple linear regression model as before and check for multicollinearity of each of these variables. Each of these variables is a continuous variable. Therefore, we don't have to worry about dummification or anything. We deal with categorical variables, so we don't have to worry about them. Apps have real-time access to your information in this meeting, whatever that means. Okay. What you could do is, in fact, you could think that something might be interacting. Some of these variables might be interacting. So you could bring in interaction terms and do the same exercises as we had done before. Okay. However, However, okay, I can see what's the chat messages. However, what we'll do is we'll first start with this simple method. Simple, these 5 variables. Okay, and we are going to do what is called stepwise regression. What is stepwise regression? We will start with a very simple model. We will use only one variable. Okay, we will use only one variable to model the world oil output. So which one of these variables can we use to model? That's the question. So what we do is we go ahead and build 5 models. One with US energy, one with the second variable, one with the third variable, fourth variable, fifth variable. Okay, 5 models we build. And then what do we see? We see which of these models does the best. Okay, so what do you mean by does the best? We can use what should I call it? We could use R squared value. That's one thing. Or we could use the P value or the T value, student T value for that particular variable. We could use that. There are multiple different ideas people use. Okay, so you have these 5 models, and of these 5 models, choose the best one using whatever criteria you use. Okay, choose the best one. Now what you do is, let us say we find that US energy happens to be the best that is world oil modeled as US energy is the best model among these 5 models. What are the 5 models? World oil modeled as US energy, world oil modeled as US auto fuel rate, world oil against US nuclear, world oil against US coal, world oil against US dry gas. Out of these 5 models, world oil against US energy, let's say, turns out to be the best one. Now what you do is take that model, add one variable to that model. So now we have 2 variable model. Okay, so how many models we will have now? We'll have 4 models now. US energy and US auto fuel rate, US energy and US nuclear, US energy and coal, US energy and dry gas. Okay, now see whether which is the best out of all these 4. Okay, and the best out of this, see whether that's still valid. What do you mean by that? Whether P value is still greater than alpha, whether R squared is reasonable, whatever numbers you are looking at. Okay, let us say US coal turns out to be the model. Okay, so world oil modeled against US energy plus US coal. Now what you do? Go ahead and add the third variable. What will it be? US energy, US coal, US auto fuel rate, US energy, US coal, US nuclear, US energy, US coal, US dry gas. See which is the best model out of these 3, and see whether this model is usable. And if it is, continue this process. Okay, and this kind of process is called stepwise regression. Okay, so here are the units given: British thermal units, US energy consumption, US nuclear energy, kilowatt hour. Okay, kilowatt hour, that seems to be wrong. That seems to be, maybe it's very small, not even in megawatt hour. So it's predominantly coal based. Short tons US coal production, total dry gas in cubic feet, not in cubic feet, cubic kilo feet maybe. Okay, fuel rate of US owned automobiles. Okay, miles per gallon. So this is the fuel efficiency. Okay, all these variables. Okay, now, so this is what we do, like what I said. So here is the first step. So world oil and 5 models, one with US energy, one with the nuclear, one with US coal, dry gas, fuel, auto fuel rate. Out of these, see which is the best model. You could use R squared, or you could use a T value. The larger the T value, the farther away it is from 0, right? And 0 is our hypothesis. So choose the T, which is the largest value. So in our case, this becomes the best model. So world oil model against US energy. Now what you do is add the second variable. So whatever the model is, this model happens to be 13.075 plus 0.580 times US energy is the world oil output. Okay. Now to this, let's add the other 4 variables one by one: US nuclear, US coal, US dry gas, US auto fuel rate. And we do this and build the model. See which is the best one. Here there are 2 contenders which are very close by: US nuclear and US auto fuel rate. 90.8, 90.06 R squared, minus 3.75 to the left side, minus 3.60 to the left side. So which is farthest away from 0? When you look at T, that's again minus 3.75. So US energy and US auto fuel rate, they happen to be the best model out of these 4 2 variable models. And P value, still everything is below 0.05. Therefore, we cannot. So we reject the null hypothesis. Null hypothesis is model is not useful or this variable does not contribute anything. Okay, so that's the null hypothesis. We reject that. Now to this, you add the next variable. So US energy, US auto fuel rate, add US nuclear, US coal, US dry gas, and you look at the p values for all of them. All of them happen to be greater than 0.05. What does it mean? We cannot reject the null hypothesis that the effect of these variables is 0. Each one of them independently 0. Right? So what does it mean? That means the best model is this one. That is world oil output modeled against US energy and US auto fuel rate. Okay, this is the kind of approach we take when other methods, like standard methods like using VIF, okay, it's not giving us any clear idea of what is happening. Okay, so this is a very, in fact, what I find is in many domains, especially in the medical side, if you see, people straight away go to stepwise regression. They use this only. In fact, I would be surprised if many of them have even heard of the term VIF. Okay, so this is the general technique that people use. Yes, Sam Leong, please go ahead.
Yes, Professor. How did you get 7.14 in the equation?
See, when you put these two variables here, you are using US energy and US auto fuel rate, right? So you use the data, use this data, and build that model.
Okay.
Build the model with these two variables. When you use only these two variables and build the model, for beta naught, we get this value. For beta naught,
okay.
Okay. When this second variable is not added, of course, things are different.
Right.
Beta naught is different. But the moment you bring in the second variable, the constant changes because you're going to a higher dimension. The constant changes. Okay. And that's why it becomes 7.14. And it's this is the coefficient for the second variable. So as the fuel efficiency goes up, the world oil output decreases. That's why the negative sign here tells you. Okay, auto fuel rate, that's the fuel efficiency. The fuel efficiency is high, then the need is lowered, therefore the production goes down a bit. Okay. Likewise, when the US energy consumption goes up, world oil output also has to go up, so you have a positive sign here. So these things make sense in that sense.
Thank you.
Okay. We could do the same thing in the reverse direction. Okay. So what we could do, we could start with put all the variables in the model, all the 5 variables in the model. Okay. And see what happens. You find the R squared for the model, F statistic for the model, whatever. Then what you do? Then remove one variable. So second step, you remove, you get 4 variables models. Okay, you have removed one variable, you have one model, another variable, another 4 variable models, so on and so forth. And see which is the best one here. And see whether the best one here is better than the previous one. If it is, then repeat the process. From the best one, start removing one variable. Repeat the process. Whenever there is no improvement, you go to the previous step and choose the best one there and use that as your model. Okay. Okay. Let me see what is. So that is a stepwise downward regression model. Okay, stepwise downward regression. Okay, so either you can go upward or you can go downward. Usually, what happens is many of these software, they do downward regression as a standard when you use stepwise regression. They use downward regression as a standard, and this is commonly used, as I told you, in the medical, clinical, and biological sites. I've always seen people use stepwise regression whenever you have multiple variables in the data. So in summary, finally, what I would like to end linear regression, that is, we are actually closing, maybe not, we are closing the chapter to some extent on linear regression, that is prediction of a value. Okay, prediction of a value. Value means the continuous variable, value of a continuous variable, and that is linear regression. So what do we do when we have a linear regression problem? This is the kind of algorithm you can say we use. Yes, Prince Dubey, please go ahead.
Sir, am I audible?
Yes. Now you are not. Prince Dubey, if you are speaking, I cannot hear you. Okay.
Sir, am I audible now?
Yes, you are. Please go ahead.
Okay. So for this step by regression, in case if I'm having a data where most of the columns or most of the features are very much correlated, is it as advisable with a step by regression?
If you know beforehand that these variables are correlated, of course, I would say don't do that. Okay.
Okay.
Like,
So
don't do
basically, sir, in finance, we never used it before, but
that.
predicting the returns for a particular stock, I see a very huge potential of utilizing it. Although I never used it before, but I'm gonna use it. But there are certain features which are very much correlated, very highly correlated. That's why I was checking whether
Never use that, because let's say as you keep adding more and more variables,
Mhm.
what would happen is artificially the performance would improve.
Mhm.
When they are correlated, instead of using the variable once, you would be using the variable more than once.
Yeah.
Right. So that will be counting the effect of a variable more than once. So that will improve the performance artificially. Therefore, this stepwise regression I would suggest only when you don't see any clarity. Your VIF is not showing any clarity. In fact, if you check in the empty cars data, my memory is that every variable will fail the VIF test.
Okay.
Okay. So, but the model itself is significant. The F statistic will give you a p-value less than 0.05. But every variable will have p-value greater than 0.05. And if you check the VAF of all the variables, almost my memory is all of them has, or maybe one, I don't remember, but one at the most or two, everything has VAF greater than 4. So you will have to drop all the variables. So that becomes very confusing. It's very difficult to understand what is happening. Therefore, in those situations, okay, we usually try this type of stepwise regression, and then what happens is we hopefully will end up with a better model. And also what we do is this: even in stepwise regression, when we reach the best model that we can, we do VIF again on the variables that are there in the model. In our case, for example, we had US energy and fuel rate. Okay, so we would check whether each one of them is independent of each other. These two are independent of each other. Okay, we'll check their correlation, and only if the correlation is poor, you should go ahead and build the model. If you don't find any other way, in every way, if it fails, okay, in real situation, this is where you would the blind algorithmic approach, when everything fails. For example, the model is good, but every variable is multi-collinear with every other variable, and you try stepwise regression, doesn't seem to give you any clear indication of what is happening. Then what you do is go add interaction terms and see if something improves there. Okay, that's the way you would approach but that's very rarely the case. Very rarely the case. We are going to see that there is another way of approaching this problem of identifying the variables that would go into the model. Okay, there we have another very powerful approach. We will get to that after we finish the next part of today's session. Okay, so in summary, when we are dealing with linear regression problems, okay, the idea is this: to start with this is your pre-processing. You need to understand the data, and any transformation you have to do, you do the transformation. Any feature engineering you have to do, you do the feature engineering. Okay, what do you mean by feature engineering? If there are categorical, so far the kind of feature engineering we have seen is, if we have a categorical variable, we do what is called one-hot encoding. We call it encoding. You can think of it as a kind of a feature engineering in a very crude way. Okay, so any cleaning the data, all these things you do. Then what you do is start fitting a regression model. Okay, then do the diagnostics on the regression model, whatever diagnostics you have to do. So usually we would do check for R squared or adjusted R squared, F parameter, F statistic for the model, that is ANOVA on the model, then t-test, student t-test on the parameters, and then check for the validity of all the assumptions and see whether there are any outliers. Okay. If it fails in any of these, okay, then what you do, it means that the model needs improvement. You go back, check the data. Okay. Usually what you do, explore data transformation once again, or check for multi-collinearity. So add or drop variables, okay, and go do with the model.
Oh my God, you have lots of process to hide your better half that nobody understand that Blazor was in Vintage luggage.
No.
Why you can carry this one?
Excuse me,
I don't know.
excuse me, whoever it is, please. Okay. I think I have muted everybody else. Okay. So, but so you keep iterating, no? Keep improving the model, and once you have reached an agreeable state, I say agreeable, not pass. Okay, because what is the purpose finally? The final end goal is to make predictions within your tolerance for errors, right? As long as your model makes predictions within the tolerance you have set for the error, that's fine, right? We are not in the process of understanding the truth. Okay, we are not in the process of understanding the truth. We are in the process of making predictions. Okay, so if that is the goal, then the moment you reach the agreeable model, you can go ahead and deploy the model. So once you deploy the model, what happens is it's not over, because after we deploy, things could change. Usually things do change. And where does the change occurs? The change occurs in the data. So with some data, we have made this model and then we started making predictions. And the predictions are for the new data, the data that the model has not seen yet. And if the new data that comes in, when the new data starts to be qualitatively different from the data that was used to build the model, then the predictions are going to be different from expected. And therefore, you will start seeing that the model is moving towards the non-agreeable region. Okay, and we call this the model drift, data drift, model drift. Okay, people use different terms, but this is one of the reasons that things will change. So what we have to do is once we deploy a model, we just don't close it and go back home. We keep observing, and as soon as the model errors start, the prediction errors start increasing, and when it reaches when it breaches the threshold we had set for the errors, then what you do, stop, include all the new data, put it back, include with the older data, and do this exercise once again. Rebuild the model, and then come up with a new agreeable model. And so this process is actually continuous. Okay, so continuous development, refinement is a process that we cannot do away with in these kind of situations. Okay, and this is one of the most elementary models we are seeing. And even with this elementary model, this continuous refinement, okay, and continuous deployment, or continual refinement and deployment is the nature of the game. Okay, we cannot escape from that. And you can imagine now, as models become more and more complicated, as you move towards more and more complicated models, specifically when you move towards neural network models and other types of very complex models, or to agentic systems, you can imagine that this thing could become a real big headache everywhere. In any kind of machine learning system, this is a big headache. So continuous monitoring, continuous integration, refinement, and redeployment is part of this entire data world that we are inheriting. Okay, so with that, what I will do is I will stop with linear regression. Linear regression is the technique of predicting the value for a continuous variable based upon the values of other variables these other variables could be continuous or categorical. Okay. So with this, we'll stop here. If you have any questions, we can discuss for a few minutes. If not, we will move on to the next. Or did I change something? What did I change here?
Sir, in a real life scenario, are there any ways to check the incoming data upfront before it feeds into the tool where the model sits?
What do you check?
So this see what in practical sense I've seen in my job is that we don't have a control on the upstream data that feeds into the models. Okay. And there could be any change that could be happening, changing the nature of the upstream data, right? So before the data enters into the model, can there be any practical monitoring or checks be implemented to ensure that the right data is entering the model for what it's about, for the purpose it is designed for?
You have described the question very well, but I'm not sure whether I understood the question equally well. Let me tell you why my understanding is why I don't understand this. Okay. The idea is this. Think about this. You built the model based upon a sample you have got. Right? Sample is all the historical data you have collected so far. Okay. But that's still a sample of what is possible in the real world. Right? And now, as you collect more and more data, so now think about this. With the original data that you had some kind of a distribution. And when more and more data comes in, see again, this is a sample, right? Your distribution might change. And when the distribution changes, your model is going to fail, right? And that's what I'm saying, essentially. Now, why do you want to check beforehand? You can check whether it falls in the same distribution or not. You can do that.
Okay.
Whether a new data that's coming in, whether it falls in the original distribution. There is a test called chi-square test. You can do that very easily. Okay, and please go check for that. And it's possible. We can do that. Now, what is the purpose of doing that? Let us say when a new data comes in, and if it is not falling in the distribution, what are you going to do with this data? Are you going to say that this model is going to spit out, or before even it goes to the model, are you going to tell whoever is the end user that this data is different, so we cannot make predictions for this? Is that what you want to tell?
So
yeah, go ahead. I'm not sure whether that's what you want.
No. So there could be a different model to handle it, and probably route this data to a different model to make it happen for the end user, to give the to make
that
the
means you have built another model as well.
Correct.
Yeah, then you have a family of models.
Correct.
Right. So if you have a family of models, then that exercise has already been done. Maybe that's part of this exercise.
Okay. Instead
of saying fit a linear regression model, maybe you have one pre-processing step here where you say split the data into different distributions and fit model for each one of them. When new data comes in, see which of this distribution this new data falls into, and then use the appropriate model. Right? That's the kind of approach you are looking at.
Got it. Thank you.
Yeah. Prince Dubey, you had a question.
Well, sir, not a question, but a real-time implementation that I have around this, because I'm having multiple models are deployed, and the way this gets the data. So basically, we have a data pipeline, and these data pipeline is actually put all the data, whatever we are getting from the different sources, into a data lake, and then the data warehouses. And that's where all the cleaning and everything which we have done earlier, and the model that is deployed, that actually goes. This warehouse is actually feeds the data to all the models, and whatever the results that which we are expecting, if that is within the threshold, as you just mentioned, are there, then we go ahead with it. Otherwise, we see the stats and see if our model is not doing exactly what we had, what threshold we have set up, then we go back and retrain it and redeploy it again.
Exactly. There is no escape from that. Okay. Yes. Mohammed Nias.
Professor, one question, like we missed a couple of minutes, few of us. You had some announcements. Could you please repeat if you don't mind?
No, the announcement is that we are not getting any extra sessions.
Okay.
What I was told was that I could extend the sessions that I already have.
Okay.
So, which is what I will have to do. And
Sure,
I'm
bro.
going to kind of go into a lecture mode rather than discussion mode for most part of the sessions, so that we could cover enough ground.
Certainly, Professor. And as there was no extra session, what we have done is like whatever was covered till last Sunday that we used for our assignments, please consider that.
Sure.
Thank you.
Okay, sure. Thank you. Okay, now what we are going to do is we're going to stop here and move on to the next. What did I do here? I did not make any change, but still it says, okay. Okay, we are going to go to a next big problem of classification. Okay, so what we'll do is we'll take a very short break. It's a change of thought process. So I would like to take a short break, 5 minutes break, and we'll come back and start on this technique called logistic regression. This is essentially a classification technique. Okay, we'll talk about this. The idea is very simple, and once we finish this, then we will go back to linear regression and talk about some more ideas of refining the models, some techniques of refining the models. Okay, so 5 minutes break, 7:20 on my watch here. We will meet once again. Okay, we now shift gear and talk about the next supervised learning problem called classification problem. Classification essentially means that if you have an object, okay, if you have an object, and if this object can be categorized, put in any of these, let's say 3 buckets, and we want to put it in that bucket such that our classification is accurate or as accurate as possible, right? Okay. So how do we do this? Mathematically, this object that we want to classify is usually given, no, it's the same variables, the x1, x2, x3, so far, whatever number of variables we have, its value is what defines this object. And the outcome variable is not a continuous function like before. It's not a continuous, it's not a continuous variable like before, but rather it's a one of these 3 classes. So the outcome variable we are going to say is one of these 3, A, B, or C, one of these 3. So we have to choose that. Right? That's what classification problem is all about. Now we are going to look at a very, very simple case of this problem, namely we have only 2 classes. Let's first start with the simplest case. We have only 2 classes. This kind of problem is called binary classification. Okay? Binary classification. Either something is in class A or is in class B. Okay? So binary classification. And remember, if it's binary, these are exclusive classes. No, if an object, that's another very important assumption. It's an implicit statement which we don't say it explicit, but it should be obvious. If an object, if one data point belongs in one class, it doesn't belong in any other class, right? So these are mutually exclusive classes. And here what we have binary classes. So these are like a class and its complement. If something is in class A, it is not in class B, and vice versa, right? So it's a binary classification. And arbitrarily, we can give the number 1 to one of these classes and 0 to the other class. So 2 classes, 0, 1. Sometimes we call them as success and failure. Success means 1, failure is 0, usually top down, whatever, positive, negative, some number, some binary terms we use to define these 2 categories without any meaning. No, we don't attach any meaning to being success or failure, just saying that these are 2 complementary classes. Where do we use? Many different situations to say whether a flight is going to be delayed or not, a person has a particular disease or not, whether a student will pass this course or not. Okay, this is another very important thing. Whether a tumor is malignant or benign, malignant or not, that's what is correct. Whether a mail is spam or not. Okay, stock moves up or down. Okay, so many such possibilities. In real life, you see a lot of different things. Quite a few of you are probably familiar with the last example and the last but one penultimate example. But these are all very common problems, right? Especially the medical examples are very common, right? So we again start with a simple example, binary classification. Okay, so what is it? And this example has been around for probably a couple of decades now. Okay, so the data is probably available online. Go and check. The idea is very simple. Now, a large auto club, for example, AAA in the US, in North America itself, right? So some auto club like that, what they do is they wanted to see whether they could introduce a supplemental health insurance plan for their members. Okay, they wanted to introduce whether they could introduce supplemental health insurance plan. And before doing anything, they want to understand whether there will be a support for such a plan. So within course, they are doing a market survey, market research within their own members, right? So what do? They send out a questionnaire and ask them to fill in their membership number, whatever details, and then ask this question, one final question. Whatever question they had one question where they asked, would you be interested in a supplemental health insurance plan? Okay. So 2 boxes, yes, no. They check either yes or no, and they collect that. Okay. And what did they do? They want to now ask the question from the results they got, so they got the results from few members. Let us say 100. Let's say they have 5 million members. First thing they are going to do is not send out these forms to all the 5 million members. That's census bad method. No, it's costly. Not do it. So they randomly select a few thousand or few hundred members and send out these questionnaires, and some people respond. Okay, and from these responses, what they want to do is they want to ask this question: if we know something about the member, can we predict whether this person will be interested in the supplemental health insurance or not? That's all. That's what they wanted to understand. Can we use the members' details, okay, and say and predict whether they will be interested in the supplemental health insurance or not? So only two states: interested, not interested. So what did they do? They looked at the data like this. Okay, so they looked at the age of their respondents because they are members, so they have that information, and they plotted the age and their interest. Those who are interested, they plotted on the vertical, they gave a y value of 1. Those who are not interested, they gave a y of 0. On the x-axis is age. I forgot to add that information here. On the x-axis is age, y-axis is 1 means interested, 0 means not interested. Now, if you look at this data, you could say a few very interesting things. Okay? You could see a few interesting things. What is it? You see, yeah, go ahead, tell, please.
There's no line.
There's no line.
Yeah, there's no line.
Correct. Even if you were to draw a line, will that make a sense? Will that make any sense?
No.
No, right? It will not make any sense. Okay. What is the value of 0. Let's say we draw a line like this, and we have a value of 0.7. What does it mean? Can be either 1 or 0, because this is just categorical variables. We just arbitrarily gave the number 1 and 0. Doesn't mean a thing. Okay. So that's not what we want. So line will not work. But few other observations we can make. Since I told you it's the x-axis age, you could clearly see in this data, young people seems like all young people are not interested in the supplemental health insurance. Obvious reason, they don't care. Young people, they have the feeling that they are invincible. They live forever as they are, so they don't care. Older people, senior citizens, no, everybody wants a supplemental health insurance, right? Because they know, they are seen, and they're already having quite a few problems in their body, mind, emotion, whatever. Okay, so they would definitely, and seems like people of advanced ages. I do not know whether you call this as advanced age. That might be offensive to some people, but for this data, we'll call it. Okay, people of advanced age, they are definitely interested. And in the intermediate ages is where we have a problem. Okay, somewhere from 45 years of age to about 55 years of age. Some people said, yes, we are interested. And some people said, we are not interested. Okay. Now this leads us to a different kind of a question. Okay. When some people say yes, and some people say no, can I ask the question, how many people said yes, and how many people said no? Definitely, that's a very interesting question. But asking that number is meaningless. Why? Because the moment I change the sample size, these numbers will change. So a more interesting question would be, what proportion of people said yes, and the remaining proportion, complementary proportion, said no? Right? That would be a better question to ask. Therefore, what we want to understand is, from this data, we see that the proportion of young people saying yes is 0. Okay, and for people of age 23 or 25 to about 42, 43, 44, the proportion of people saying yes is 0, whereas proportion of people saying yes, people of ages 55 and above, is actually 1. And between 45 and 55, it goes from 0 and it's some number between 0 and 1. And because it's proportion. Proportion is it has a different name in our field. We call that probability. So now we can relate easily. The probability that somebody of age 33 will say yes is 0. The probability somebody of age 47 will say yes is maybe 0.4. Okay. Probability somebody of age 70 will say yes is 1. Right? So we have that. So now what we can do, we have age on the x-axis and treat this as probability values. Probability is a continuous function because it can have any number between 0 and 1. Therefore, we can build a model. We can now draw a line. Now that line makes sense. But that line cannot go beyond 1 and that line cannot go below 0. Not only that, that line cannot be just a straight line because we need to have a line that looks like this. Right? We need to have a line that looks like this. So the probability that somebody will say yes is a non-linear function. It's not a straight line. Right? It's a non-linear function. And this kind of curve, as you can clearly see, looks like a distorted S. Distorted S. Right? So it's called the S curve. S curve. This is also called the psychometric function. It is also called the logistic function. That is where the name of this model comes in, logistic regression model. So it's a logistic function. It is also called ogive. I do not know the origin of this name, ogive. This is what psychologists use, specifically people who do mathematical psychology, who come up with these crazy formulas. Those are the people who use the word ogive. Psychometric functions, econometric functions, any metric functions between two binary variables, S curve or logistic function, multiple names this has. And the mathematical form of this is the predicted probability. We are going to predict the probability, right? We are not just saying probability. So we are going to predict the probability that something has a value. Age has for age of some number, the predicted probability that this person will be in class 1, that's given by this horrible looking mathematical expression. Okay? But don't worry about it. It's actually very easy. E power some number divided by 1 plus e power some number. Okay? So it's actually quite symmetric, if you can see this. What is E? E is a very crazy number. It's something like 2.71828 data. I don't remember anything beyond that. It's like pi. Pi is a number which is like 3.14159 something, right? So it's like that. This is called an irrational number. You cannot represent it as a ratio of 2 integers. We cannot do that. Okay? So there are infinity of irrational numbers. We have name for a few of them. One of them is pi. The other one is E. I don't remember any other irrational number that has been named. Maybe there are some, but I don't know the name. Okay. So this is e power something. What is the something? That something is a linear function of the variable. What is the variable in our case? The variable in our case is age. So e power beta naught plus beta 1 times age divided by 1 plus e power beta naught plus beta 1 times age. That's the model we have for the predicted probability that that person is in class 1. Okay. So what? There is some math equation. So what? Okay. So, okay, this has to be hat. This is not just probability. This has to be predicted probability because we are building a model for the probability, right? It can be a single variable or multiple. If it's a there are many variables, then you put all of them like this here. Put all of them like this here. You already see where we are going. Regression, logistic. This is the logistic function. Here you can see some form that looks like the regression, linear regression form. Therefore, this is the logistic regression. Okay, that's what it is. Now some definitions. Okay. Yes, Suvir Bajaj, please go ahead.
Sir, is it possible to go one slide back, please? So in this slide, the formula states 1 over 1 plus e raised to negative mu And in the next slide, okay, I'll wait for you to explain it before I ask my question.
Okay, so e power anything power minus something, in this case e power negative mu is the same as 1 over e power plus mu. Okay.
Got it. Thank you.
So let me do one thing. Let me do a new slide. Delete this, go here, copy this, paste this here. So what happens is, okay, let me do simple. Control C, Control V. Now this becomes 1 over plus this is what this is 1. So since e power minus mu is 1 over e power mu, it becomes like this. This thing we can rewrite again, right? Yes. This thing we can rewrite as 1 over e power mu plus 1 over e power and no, not this. This looks so this has to be like this, right? So I cross multiply 1 plus e per mu by e per mu. Now our standard thing is this is nothing but 1 over something is the reciprocal of that something. You have to reciprocal this, right? It's a reciprocal of the reciprocal of this. So e power mu goes up. Therefore, this becomes, so this becomes this is equal to e power mu over 1 plus e power. Okay. So these two are equivalent. So this is the math involved here. Is that fine? Was that the question?
Yeah, yes, thank you.
Okay, sure. So now we go to the very basic probability question, that if the probability of being in class 1 is something, what is the probability of being in class 0? That would be 1 minus that something, right? It would be the probability of being in class 0 is 1 minus p, where p is the probability of being in class 1. Okay. So when you do that, okay, again you have to do the reverse of what we did in the previous slide. So this will become 1 plus e power something minus e power something, the whole divided by 1 plus e power something. Okay. So this becomes something like this, because there is 1 plus e minus e, therefore plus and minus cancel. So the numerator has 1, the denominator has this. Okay. So 1 plus e power something. This is what is the probability that the data is in class 0. Class 1, this is the probability. Class 0, this is the probability. Okay. This is simple math algebra again. Now, if you take the ratio of these two, p divided by q, probability in class 1 divided by probability in class 0. Okay. To take this, what do we get? This thing divided by this thing. So the denominators gets cancelled. Therefore, we get p over 1 minus p is e power something. This form. Okay. So what is this? This is probability of success. Usually people say this way: probability of success divided by probability of failure. There's a possibility you might have heard this term, this ratio. This ratio is called odds. This ratio is called odds. Odds is probability of success divided by probability of failure. So the odds that something is in class 1 is given by this expression. Okay, we call this odds. Okay. It's very easy to go from odds to the probability. In fact, let's do that. I do not know whether I have done that in the next slide. I have not done that, so let's do that. Okay. Let me check. I might have done that in the next slide. Okay, I've not done that. So let's do that. Okay. So new slide. What happened? Go here. So let me do this. So odds is given as P over 1 minus P. Okay. Let's do a simple math of this. So this would make it look like S times 1 minus P is equal to P, S times, sorry, 1 minus P. Now when you cross multiply, that's what we get. So what does this lead to? This leads to SP, sorry, S minus SP is equal to P. I'm just doing simple math here. So what do I want? I want to collect P all in the same place. Okay. So this becomes S is equal to SP plus P. Okay. I'm just bringing this SP to the right side. So this becomes S is equal to SP plus P. Now, what do I do? I say yeah. So this S is equal to P times 1 plus S. Right? So P times 1 plus S. Therefore, P is equal to S over 1 plus S. So you see very symmetric relationships, right? So we have P in terms of odds in terms of P. Okay, they look very similar, just the change of the sign here. Okay, so yes, which is odds, is probability of success divided by probability of failure. Probability is odds over 1 plus odds. Okay, so this very symmetric relationship you would see. Okay, so what? So what I'm interested in is not this relationship actually, okay, but something much different. Okay, you see, yes, Sam Liang, please go ahead.
Yeah, we have used the word odds in our conversation before. So let's say if someone were to ask us, what are the odds that a student completes the GGU DBA program? I repeat, what are the odds that a student completes the GGU DBA program? How do I go about using this formula to answer?
Well, you will have to excuse me for being a geek.
Okay.
I have always never understood questions like that. In fact, if you remember in the very beginning of the course, I would have said I would try to avoid the use of the word complex, because in mathematics, complex has a very specific meaning. Likewise, after I have learned these concepts, these terminologies, I avoid using those terms like odds. What is the odd of something happening? People usually think about probability and they wrongly use the word odds. Okay? But the actual meaning of odds is this. In fact, in horse racing or gambling, when people say odds, which is a very technical, it's a, I don't know if I can call it a profession, okay, professional gambling, professional betting, odds there has this exact meaning, P over 1 minus P. Probability is never a number beyond 100%, but odds can go way beyond 100%. In fact, you would have seen 10 million to 1, 10,000 to 1, or 1 to 10,000. That's what people say. When people say odds, they usually say the odds of this team winning this championship is 1:5. That's what people usually say. That means they're talking about this probability. 1 over 5 is the odds they are talking about. Okay. So,
okay.
So that's the only meaning of the words odds that I know of. So I'll just stick with that.
Thank you.
Okay. Now, why am I doing all this mathematical jugglery? Because I can go, okay, here is some example, some more explanation of what is odds is defined as probability of success over probability of failure. When everything is at class 1, when P is 1, then odds is infinity. No, odds tends to infinity. That is, everything is there, infinite odds. Okay? When probability of success is 0, then odds is undefined. It's very close to 0. It's undefined. It's actually, yeah, it's close to minus infinity, but it's undefined. This is also, we should say, tends to plus infinity. This also we can say tends to minus infinity. But this is undefined. 0 by 1, 0 by any number is undefined. You cannot divide 0 into any number of unknown divisions. When odds is when probability is 0.5, halfway, this is a very interesting situation. Odds is 1. Odds is 1. Okay. So what does it mean? Why are we doing this? We are doing this because we can now, when we wrote odds as e power something from our logistic regression equation, if that is the case, if you take the logarithm of odds, e and log are like inverse functions. Okay. If you take logarithm of this number, logarithm of e power something, then you get just that something. Okay. So if you take the logarithm of odds, that will be equal to the exponent here, beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth. If you look at this equation, this should look like your linear regression, right? This should look like linear regression. And that is why we use the term logistic regression. It's not a linear regression, but it's a logistic regression. Okay. So what we are going to do, we are going to fit a model for this. What does it? What do you mean by that? We are going to do something to this logarithm of s such that we get the optimal value for beta naught, beta 1, beta 2, etc. Okay. That's what we are going to do. What is that something we are going to do? That something we are going to do is a slightly new concept. I want you to pay attention to this for some time. As per third, probability of pass divided by probability of failure. If you say 80% pass and 20% failure, then the odds is 4. This means student is 4 times more likely to pass than fail. Exactly, John Sirani. Very correct. So we are very confident we have likely 4 times likely to pass. Correct. Very correct. Right. Now, let's see that now the idea is, in any model building exercise, these are the parameters. Building the model means finding the values of these parameters such that some metric is optimized. In linear regression, I will not even call some metric, some cost function. Okay, some function is optimized. Okay, or some cost function is minimized. Cost is minimized. That's what we want to do. Okay, what is the cost here? Earlier we had y hat is equal to beta naught, beta 1, so on, and then we had the cost function to be sum of squared errors. Okay, here we have y hat is equal to beta naught, beta 1, etc., where y hat is logarithm of odds. Okay, but can we use sum of squared errors? We cannot. Why? Because we have no measured values of odds. We have no measured values of logarithm of odds. We are working in the probability world. We are not working in the actual measurement value. There is no measurement per se except categorization. The most we could use is how accurate is our categorization. Okay. Am I putting all zeros? Does my model also put it in class 0? Am I putting all my ones also in class 1? But this is not about that, right? This is about probability. We do not know that, what to do with this. So we go to a new concept called likelihood function. Okay, we go to something called a likelihood function. This is a kind of a very difficult, I mean, might be a slightly confusing idea, but think of it this way. Okay, the idea is this. Let's say we have a distribution. Okay, a distribution. And then from the distribution, we would say, okay, what is the probability of getting this value? That we can get from the distribution. Now look at the other way. I have the value, the probability of getting this value is some number. Okay. So what distribution do I have? Okay. That's the kind of question we ask. Okay. So what is the likelihood that this data might have come from some distribution? That's the kind of question people ask when people talk about likelihood function. Yes, Suvir, please go ahead.
So just to create a some continuity, is the likelihood function still under the same theme of binary? Are we still under the same theme by itself? We're not.
Likelihood function is a continuous function.
Okay, got it.
Okay. But in this case, it's more like a, yeah, it's a continuous function. Okay. So it is not binary. But what we are going to do is, this is the reasoning we are going to do. Okay. At the end of the day, okay, when you have a model and the model gives you some probability, for given age, for age 35, it gives some probability. Okay, let's say it gives a probability of 0.89, very close to 1. But actually, your data is 0. Your actual probability is 0. But let's say it gives 89. Okay, or that's another case where for 33, it gives a value for age 33, it gives a probability of, let us say, 0.05, very close to 0, whatever it is, right? So now what we want to do is, we want to create a function. We want to see that in the ideal, when you have optimized the function, okay, for every data point that is in class 0, we should get a probability value close to 0, and the complementary probability should be close to 1. Likewise, and for every point that is in class 1, we should get a probability value, predicted probability value, close to 1. Okay, and its complementary probability should be close to 0. Right? When you talk about probability, and we started with the assumption, look at all the assumptions for logistic regression, it's still the same as the assumptions for linear regressions. What is it? They come from normal distribution, the homoscedasticity is there, the measurements are independent, and that's a very important characteristic. If the measurements are independent, then the first measurement, if a data point is in class 0, its predicted probability is also class 0, and if the complementary probability is 1, and for the next point, and we get all these ands, and for independent measurements, independent values, translates in probability to be multiplications, and that is what I have given here. For a given point, for any given point, for I is equal to 1, okay, I have the predicted probability y, okay, and its complementary probability to be 1 minus yi. Okay, and this is the case for every point. This yi, predicted probability yi hat, can be 0, in which case all these things could be 0, or it could be 1, in which case all these things could be 0. Okay, of course, we are going to get values that are close to 0 because we are estimating, so we don't hope it to be 0. Okay, so for each point, since we are doing it, for each point, that point's class value, actual class, becomes the exponent. Yes, go ahead, Suvir Bajaj.
So is it possible to explain the use case of this function prior to going into formulation? Why would we use this in practical terms?
See, essentially, what we want to do, the idea is this, okay? Let's not worry about the formulation. We can forget the formulation. You have a very good point. We cannot use sum of squared errors like what we used in linear regression, because we are not in the error situation. We are in the probability situation. In probability situation, what can we do? The predicted probability should be close to the actual probability when the model has been optimized. When you have got the optimal model, the predicted probability should be close to the actual probability. Right? That's all we want. And that is captured by this horrible looking expression. Okay. This symbol pi here means product. Okay, it's a product. Okay. So just think of it this way. Okay. All this is saying is, when a data point's actual value, actual class is 0, the predicted probability should also be close to 0. That's what we are trying to say here. Okay. Now, since the products of numbers are difficult to handle, and so we change them into summation of numbers. And how do products can be changed to sum when we take the logarithm? When we take the logarithm. Okay. And if you look in this is again a very interesting formulation. Okay. But you could see, yi is the actual class. It's either 0 or it's 1. Okay. So the coefficients are usually 0 or 1. Whenever they are 1, then whatever is in this logarithm will only have a value. Right? Will only have a value. So now, if you take this function, okay, this function is what is called a concave function. Called a concave function. What is a concave function? Concave function is a function that looks like an inverted U. Okay, it looks like an inverted U. Okay. Yes, Prince Dubey, go ahead.
That one thing, most of the time, this likelihood functions I have seen generally we use when the data, when the sample or the data that I have, it follows the normal distribution, right?
Yes.
But can I apply this this function if my data is not normal?
In general, yes. Okay, in general, yes. The reason is this likelihood function does not assume anything about the distribution of the data. Okay. Many a time we deal with the normal distribution, but likelihood function is much more stronger than that expectation. So you could actually do that.
Okay, perfect.
Okay. And what we want to do is usually we do minimization, because reaching the minimum is easier mathematically than reaching the maximum. And so what we do is take the negative of that. Instead of inverted U, you flip it, make it a U. How do we do that? Put a negative sign in front of it. So this equation is called negative log likelihood function. Negative log likelihood function. We want to minimize the negative log likelihood function. And this is a very easy problem. It's a very easy problem. Why is it a very easy problem? It's a U. If it's a U, you always know that there is a minimum. Not only that, there is only one minimum. In a U, there is only one minimum, not multiple minima. So this is a very powerful cost function we can use, because it guarantees one and only one minimum. Okay. So what do? We start with the star. Well, we start with how do we now fit the model? What do we do is we start with some arbitrary values of beta naught, beta 1, beta 2, the parameter values. Calculate the logarithm of odds. Okay. From the logarithm of odds, calculate the probability, because logarithm of odds, from logarithm of odds you can calculate the odds. From the odds you can calculate probability. Once you know the probability, calculate the negative log likelihood function. So you have some value. Now what do? Go and change the values of the parameters. So change the values of parameters. How do we change? Use a step size. What step size? We do not know. That's a hyperparameter, the learning rate, which we have to fix. Then should I increase the values of the parameters or decrease? You use the gradient descent technique. I have not told you what that is, but there is a technique that tells you which direction we have to go. Okay, we will talk about this maybe later in this course, or definitely in the next course we will talk about that. Okay, gradient descent technique. So what do? Change the values of the parameters, and then what you do? You would calculate the logarithm of odds. From the logarithm of odds, calculate the odds. From the odds, calculate the probability. From the probability, calculate the negative of the log likelihood function. See whether it has decreased. If it has decreased, repeat the process until it reaches a minimum value. How do you know it has reached the minimum value? You know, because at some point it starts to increase. Once it starts to increase, you stop there, go back one step and use that. Whatever parameter values are there at that point, that's your optimal values. Okay, so that's what we will do in terms of estimating the parameters. So estimating the parameters is no different. It's the same thing like before. Use the gradient descent technique. Instead of sum of squared errors, we are just using negative of the log likelihood function. Okay, so here's the example. So what did we do? I did this model building for this. It's an old screenshot from for this data. I did this in Python. No, and here is the screenshot of that. And you can see now some code. Don't worry about the code. Let's look at the logistic regression results. Let's come down to the model. Okay, it says more coefficient, constant, coefficient of the age. Right. So what do we have? The model is minus 20.41 plus 0.43 times age. That's what the model is. What is the model for? The model is for the logarithm of odds that this person will say yes. That's what the model is. Okay. So let's forget about the code. Okay. Let's look at something called the logistic regression model. It gives you something called a LLR p-value. You can immediately guess what is LLR. Log likelihood ratio. Okay. Ratio of what? The moment you think about ratio, you can immediately think of something in linear regression. We use the ratio to test the model, the F statistic. Remember the F statistic? That was a ratio of two variances, regression over residual. Likewise here, we have two log likelihood function values. What are the two log likelihood function values? One log likelihood function value using the model. With the model, what is the value we get? Log likelihood function value. Then there is one model with, there is one log likelihood function value without the model. No, when age is 0, without the model. What is that we get? So take the ratio of these two, okay, and that will be a statistic. Do this and then calculate the p-value. You see the p-value is practically 0 for the model, which is good. Then you look at the parameter space. All the p-values are less than 0, less than 0.05, practically 0. Therefore, this model is agreeable, workable, usable. Right? Excellent. What is the equation? The equation is logarithm of odds. That's what we are modeling. That's what the parameters talk about, right? Logarithm of odds is equal to minus 20.41 plus 0.4259 times age. Okay. What does it mean? What I want to know is, what is the class? Will a person of age 55 or 51 or 50, let us say, a person aged 50, will this person say yes or no to this supplemental health insurance? That's what I want to know. How do I do that? All I can say is, with this model, all I can say is, what is the probability that this person will say yes? Right? Why? Because from logarithm of odds, I substitute the age here. So when I substitute the age, so 0.50 times 0.4, so that will be 0.2 something. Okay. Sorry, 20 point something. So that will be some number here. So that will be the logarithm of odds. From logarithm of odds, calculate odds. From odds, calculate probability. And that probability I can find. That's what I can do with this model. Right? So here I substitute. So logarithm of odds becomes 0.88 to 8872. Okay. Therefore, odds becomes 2.4281. Okay, which is e power logarithm of odds. Now, since I know odds is equal to p over 1 minus p, therefore I can calculate p. P is equal to odds over 1 plus odds. Right? Odds over 1 plus odds. When I do that, probability that this person will say yes is 0.71. Okay. This is not the question I asked. The question I want to ask is whether this person is going to say yes or no. Okay. But I'm giving it an answer. The probability that this person will say yes is 0.71. What can we do now? Now we have to look at this probability and see, is this probability high? That's the question we ask. Is this probability high? If this probability is high, I will put this person in class 1. Why? Because we are calculating the probability for class 1, the upper class, not the lower class. Right? So we are calculating the probability to be in class 1. That's what we are calculating. If this probability happens to be high, then I will put this person in class 1. If it is not high, I'll put this person in class 0. So what is high? What is not high? That is something we have to decide. We have to decide. The model does not do. Right? So we have to set a threshold for this categorization problem. So you see, this logistic regression, in fact, in all classification problems, this is a two-stage process, two-step process. You build a model for something. In this case, we build a model for the probability. That's what in most cases we are going to do. We build the model for the probability and then set thresholds for the probability. Second stage. If the probability is greater than some number, put it in class 1. If not, put it in class 0. Okay, this is what we do. So we have to set a threshold. In this case, there is no in an unbiased, if it's an unbiased situation, we would say halfway through between 0 and 1. That could be a good threshold for classifying in class 1 or 0. That's a logical approach. So this number is closer to 1 than to 0. Therefore, we say this person will say yes. That's what we are going to model. We are going to say that this person will say yes to the supplemental health insurance. Okay. So this is how we do logistic regression. Okay. So here is this much better graph. This is drawn with the data, with the model. And here is the 50%. That's the threshold on the probability. So if the probability is greater than 0.5, the probability is in this region, I will put them in class 1. If the probability is below this dashed line, I'll put them in class 0. Okay. But you see, I can do it this way. In our case, all ages greater than this 48 years, they all have probability value greater than 0.5. So now, instead of setting the probability threshold on the probability, I set the threshold on the variable itself. I set the threshold on the variable. So now, you see, I have a classification boundary in the feature space. In the feature space itself, I have a classification boundary. I put this line. So anything to the right, I will classify to be in class 1. Anything to the left, I will classify it to class 0. Okay? So we define a boundary in the feature space. Now, if I change, for example, in psychology, for example, in psychometrics, many places, in classical sciences, people never accept 0.5 as the threshold for probability. Why? I can close my eyes or keep your eyes open, do a coin toss, and whenever you get head, you put in class 1. Whenever you get tail, put in class 0. Doesn't care about what happens. Okay. The probability that you will get success is 50% there. So that's therefore it's like a random classification. Even in random classification, you'll get 50% success. So we don't want this. So what they usually do is they keep a higher probability threshold. So if you want to keep a higher probability threshold, what could be a higher probability threshold? Halfway between 0.5 and 1, which is 0.75, right? So that's what some people use. If you use that, then your boundary shifts to a new position, right? Your boundary shifts to a new position. So we can decide the boundary, we can determine the boundary based upon the probability threshold we want to use. Okay, and this is in your hands. You can choose this probability threshold. Okay. Here's another example. I'm not going to go through all the details here. What we want to do is same empty course data, the same data set.
So doctor,
Go
see
ahead.
me? So when you say the example flipping the coin, so it's totally a random pattern of yes or no, right? Or head or tail, right?
Yeah.
And if we facing that kind of data, what will you do? You just say that we avoiding that by shipping the higher threshold, right? But can you explain that one? How can that solving the random pattern of the data?
See, think about this. We are talking about for a single individual. You know, using a toss of a coin, you either get 0 or 1. 50% of getting class 0, 50% of getting class 1. Okay, so the error rate there is 50%. Okay, because just a toss of a coin. If you want to reduce that error rate, you need to do better than 50%. So what do we do? So you reduce this error region by this much, or by this much actually. And that's what we are doing there. This is for not for the entire data. In fact, that's what it will come out to be. So if you have like 50 data points, and for each point you have a probability of success to be 50 and probability of success to be failure is also 50%. Okay, then when you put all these 50 data points, you will get for about 25 of them you will get correct classification. For 25 of them you will get poor classification. Okay, so your accuracy, overall accuracy, will still remain 50%. We don't want to do that. Okay, so that's why people usually change this classification boundary. Now, just keep that in mind. Let's not go too beyond that, because this thing has a much bigger role to play. Identifying the classification boundary has a much bigger role to play. We'll come to that in a very short while. Okay, before that, let's take another example. Here is an example where we are plotting the horsepower and the weight of these cars, okay, of all these cars. And there are two types of cars, right? Automatic and manual transmission. Okay, so in this diagram, now we have just did a scatter plot of the braking horsepower and the weight in thousands of pounds. And when you see which cars are which data point is which type of transmission, this is what we get. All these red ones are manual, and all the blue ones are automatic. Okay, all the blue ones are automatic, all the red ones are manual. Okay. Now, if you see, no, is there a boundary here? Yes, of course there's a boundary. Can we figure that out? Yes, we can figure that out. How can we figure that out? So we do so either something is in automatic, let's say class 0, or manual, which is class 1, let us say. So you build this model, that is some probability that something is going to be manual is the logarithm of odds that something is going to be manual is equal to beta naught plus beta 1 weight plus beta 2 horsepower. That's what we are going to do, right? So you build that model plainly, weight, horsepower, and this thing. You build the model, you get some equation. What is the equation? The equation we get is logarithm of odds. So don't look at this equation. So this is the equation we get. The logarithm of odds is 18.86. Logarithm of odds of being in class 1. What is the class 1 here? Manual. Yes, 18.86 minus 8 times weight plus 0.036 times horsepower. That's what we get. Okay. Now what we can do, okay, we can set logarithm of odds to be 0. If logarithm of odds is 0, then odds becomes 1. If odds becomes 1, probability is 0.5. So probability is 0.5 means odds is 1, because 1 over 1 minus 0.5. So 1 over 0.5 over 1 minus 0.5. Therefore, you get odds to be 1. Logarithm of odds is 0. So it becomes 0. So if it is 0, then what do we get? We get this equation. Minus, you can bring this here, minus 18.86 plus 8.0 something is equal to 0.3636 HP. Okay, or you divide this throughout by 0.03636. So HP is equal to this number times weight plus this number. Y is equal to mx plus c, straight line, right? So you get something like this. So y, in our case, y is HP is equal to mx, this is the slope, plus c, somewhere here is the y-intercept. So this is the line. So you have a line, straight line. It's not a curved line. The boundary is a straight line, right? Anything to the right is the blue. That's what we classify. That is, anything to the right is automatic. Yeah, it's automatic. Yeah, and anything to the left is manual. Okay, anything to the left is manual. So this is what we are saying. So you can define the boundary by setting the probability. If you change the probability, let's say I don't want probability to be 0.5. I want the probability threshold to be 0.75. If you say that, then our odds will become 0.75 divided by 1 minus 0.75, that will be 0.25. So odds will become 3. Then logarithm of odds will be some number, 1 point something. Logarithm of odds will be some number, 1 point something. So what will you have? 1 point something is equal to 18.8663 minus this plus this. Again, you can come to an equation like this, but these two numbers will be different. Right? This number will not change, slope will not change, but the y-intercept will change. What does it mean? this line will move to the right or to the left, depending upon what the logarithm of odds is. Okay, so this will move to the left. So if you change your probability threshold, like in the previous case, how it moved to the right, this will also move to the right. Okay, so move to the right. So now what happens? Therefore, you can change the boundary for classification by changing this probability threshold. Right? This is what we do in generally. Now think about this. This is again a constraint problem. Only two variables. In reality, your data might have 20 or 3,000 variables. So that's going to be multi-dimensional space. In that multi-dimensional space, you have to draw a boundary. That's going to be a plane in a multi-dimensional space. It is not going to be a surface, curved surface. It's going to be a plane. We call it a hyperplane in multi-dimension. No, it's a plane. If it's a plane, on the one side you have class 0, on the other side you have class 1. That's all. Okay? So we can always do this division of this feature space into two areas by a linear surface. That's a planar surface, plane or a straight line. Okay, and that is why it's called a linear classifier. Linear classifier. The boundary is fixed not by the model. The boundary is fixed by us by setting a threshold on the probability value. That's how we do the classification. Yes, John Sirani, please go ahead.
Yes, Rajan sir, you're mentioning boundary is fixed by us. Imagine like we are not the domain experts. Of course, if we are saying like medical domain, so if I use this boundary, I always choose the lower. Like if the prediction probability is telling 0.3 also, yeah. But
let me
if
jump ahead of your question.
Yeah,
we are moving towards finding an objective way of fixing the boundary.
Okay, good.
Okay?
Yeah.
We are going to do that. Okay.
Thank
So
you.
we are
Thank
going
you.
to take an example from medical side. It's called Framingham Heart Disease Study. We will discuss this in some detail, and we are going to show some deficiencies or some challenges we cannot escape when we do logistic regression or any kind of this binary classification, and we will see how we can identify an objective boundary. Okay, that's what we are moving towards. That's our next step.
Beautiful. Yeah,
Once we identify that, the problem is over. We have a model and we have an objective boundary, so we got a clear classification scheme. Okay, that's what we are going to do. So what we will do is we will take a short break now. Time now on my watch here is 8:33 p.m. So 8:45 on my watch, we will meet again. Something like 12 minutes from now, we will meet. Okay, so take a short break, please. Thank you. Please give me 1 more minute. I'll be back in a minute. Thank you for your patience. Let's start. Okay. So this is a very interesting study. It's still ongoing, but initially when they started it, it was planned for a few years. Okay. Specifically, what they wanted to do was they wanted to study with Boston University. Now they wanted to study. They wanted to know whether they could predict who will get a heart attack. They call it cardiovascular disease. So cardiovascular disease in the next 10 years. Okay, so can we predict that? That's the kind of question they were asking. So they did not start with that. They just asked question, what are the risk factors for cardiovascular disease? Okay, and they wanted to study it for a long time because these things happen at a slow pace, therefore slow rate. Therefore, they wanted to study over a long period of time. And those kinds of studies, these are called longitudinal studies. These are very difficult to conduct. Why? Because people migrate, people die, new people move in, new people are born. Right? So multiple things can happen. So what these people do, they chose this town called Framingham in Massachusetts, which was pretty much an isolated town. It's static in the sense there was not much of a movement in or out of this town. So they chose this city, and then a town, and then approximately, they collected 2/3 of the population aged 30 and above, or I think it's 30 and above, yeah. And they collected data from these people, and totally there were 5,209 men and women who participated. But then it kind of went down when the final data was collated to do the analysis. So what was the thing they wanted to do? They wanted to study what risk factors are there for the incidence of cardiovascular disease. So what leads to cardiovascular disease? That's a kind of question they were asking. Okay. And you could there are a couple of links I've given here in the slide deck. I'll upload these slides anyway today, so you could go ahead and check them. And what happens is you could go and you fill out all the different parameters and see what is your if you're curious, what is the probability that you will have a cardiovascular event in the next 10 years. Okay, so what happens is that they collected data from approximately 4,240 individuals. They made 15 predictor variables and 1 outcome variable. 1 outcome variable only after 10 years. Okay, at the baseline, starting now in 1948, 15 predictors. What are these? Data like gender, age, education, then whether they were smokers or not, and how many cigarettes they smoked per day, whether they were taking BP medications, was there stroke, whether they had hypertension, whether they had diabetes. I don't remember how they defined diabetes in those days. And then all these different things: total cholesterol, systolic blood pressure, diastolic blood pressure, body mass index, heart rate, and blood glucose level. I think there was an random blood glucose level. Okay. So this is what they collected all this data. And then with that, then they observed people for 10 years and found out who all had heart disease in the 10 years period. Okay. Then what they can do, for each person they have this data, then they can build a model. In 10 years, somebody developed a heart disease, yes, no, 2 categories, based upon all these 15 variables. So this is a very natural data set yielding to logistic regression. Okay. So this is one approach we did not talk about this in linear regression, but this is generally the approach we take. What it is when you have data, we don't use the entire data to build a model. Why? Because we want to know whether the model works correctly or not. Okay. For new data, we really do not know. So in the data that we have, we use a large chunk, usually 70 to 80% of the data that we have. We use that chunk, randomly selected 70 or 80% of the data, to build the models. This is called the training set. The 70 or 80% of the data that we are using to build the model, that's called the training set. And the remaining 30 or 20% is called the test set. So we build the model with the 70 or 80% of the data. Once we have got to the best model that we could get to, we use that to see how this model is actually doing on data that has not been seen. Right? So this the test set is the data that the model has not seen. So we check it on the test set to see how well it does. If it does well defined whichever way, okay, then you go and use the model. If not, go back and see what you're missing, rebuild the models, right? Okay. So we randomly split the data, Framingham heart disease study also, into 70-30. Okay. And then when we split the data, especially for example, when we split the data into 70-30, let's say, we got to be careful. Why? See, not everybody, not even 50% of the population is going to develop heart disease in the 10 years. Okay. Some small proportion is going to develop the heart disease. Let us say 20% of the population develops heart disease in 10 years time. Okay. When we do this random split 70-30, what if all the 20% belongs in the test set? That would be a disaster. Why? Because the training set will not see any disease people at all. Likewise, if all the tests go into the training set, again, it will not be able to make accurate predictions in the test set. So what we need to do is we have to split the data into training set and test set such that the training set, the test set, and the overall data have the same proportion of these classes. Okay. So if 20% is in the total data set, then the test set should also have 20% of the test set should be people who develop the disease. 20% of the training set should also be people who develop the disease. That's how we have to do the splitting. And that's a very important catch that we have to be clear about. Okay. So we do that. Okay. Let's say we do that. Now, once we do that, we check in this data, we check that what is the proportion of people with the disease in the test set and also in the train set. So in the train set, the proportion is 15.12%. 15.12% of the train set develop the disease in 10 years. Likewise, in the test set, 15.48% develop the disease in 10 years. So approximately equal. This is fairly good. Okay. Now, here is the catch. We built the model. Here is a model that we built. Okay. So same thing like before. Put everything and then build the model. You look at the likelihood ratio p-value, practically 0. So the model is agreeable. So we do not reject the model. Yeah, we reject the null hypothesis. And then now look at the parameters. Which are all the parameters that have p-value greater than 0.05. So these are all the parameters that have p-values greater than 0.05. So what do? We drop these parameters and then rebuild the model. Okay. Of course, if you see the significant parameters, the parameters that stay, they are gender, age, prevalence of prevalence of hypertension, total cholesterol, systolic blood pressure. Okay, same thing, hypertension prevalence and systolic blood pressure. These probably are correlated, right? Then glucose level, right? These are all there. So we read in only those and throw away all the ones that have p-values greater than 0.05 and rebuild the model. Now you check again, p-value practically 0 for the model, and we still find one parameter, cholesterol, okay, which has a p-value greater than 0.05. This is very interesting, actually. This is data coming from the 1950s and 60s, right? 48 to 58. Now, even in that data, compared to modern day methods, this would have been poor. But even with that data, you see, cholesterol is not a good predictor of heart disease. Okay, and this is known from when actual studies started happening. But the epidemic of statin consumption, okay, is very high. If there is any cardiologist in the group or anyone related to a cardiologist or knows a cardiologist, they might be frowning at me for saying this. But for the last, I remember in the 1990s when maybe it was Pfizer who started with Lipitor. Okay, those were the first drugs that came into the market to control total cholesterol. So this is something we have to pay attention to. The data clearly says cholesterol, at least this data clearly says, one of the largest and reliable data sets says cholesterol is not a risk factor for heart disease. Anyway, so we remove that and rebuild the model. Now you see everything is fine. All the parameters are they have p-values less than alpha. Therefore, we can go ahead and use these parameters. What are these parameters? Gender. Okay. Then age as the positive. So as the age increases, then you have a higher chance of getting this. If it's male, then you have higher odds of getting the disease, prevalence of hypertension, systolic blood pressure, glucose, all these things, right? Now, with this model, we make predictions on the test set. Both we check on the training as well as the test set. Okay. So with this model, we look at we see what percentage of training data we predicted accurately. Okay, accurate. So we saw this 85% in the training set. Okay, what is it? That is 85% of the people are corrected. If somebody had disease, they were classified as disease, and somebody did not have disease, they were classified as not having disease, and together the correct predictions was 85% in the training set. How about in the test set? Again, you see it's 85%. 85%. Now look at all this these decimal places, ridiculous. My own error. Okay, but 85%. Okay, both training set and the test set, the accuracy of classification is 85%. Okay, now the question I ask you is this a good model or not? 85% accuracy. Is it a good model or not?
Yes.
Yes. Okay. Nimesh says yes. Anybody else?
I think this will be based on what we expected from the prediction results. For example, if we set the error, the acceptance error rate, the 5% is much higher than 95% of accuracy. Must be a good acceptable model.
So essentially, you are saying this is not a good model.
I am saying, I mean, if I set the threshold of acceptance error, repeatability error, I mean, 20% is a good, but if I set it to 5%, it's not good model.
Okay, it depends upon what your tolerance of error is. That's what you're saying. Okay,
yeah,
Sam,
yes.
please go ahead.
The fact that the training accuracy is very close to the value of the test accuracy, then we can say this is a good model.
Very good. Okay, two more people. I don't know who the other two. Please go ahead.
Yes, sir. So looking at the testing and training accuracy, it looked like that model was able to generalize the data in whatever we have given it in training as well as in testing, and it looks very close to each other. So this model looks very good. And anything I would go,
Okay.
if
Good,
anything,
good.
above 8%, 80%.
Okay, very good. Now let me do one more. I'm going to give you one more model. Okay, this model is called blind Rajan model. Okay, what blind Rajan is going to do is sit with his eyes closed, and whichever people from this data set you bring to me, I am going to classify as not disease. Okay, no disease, no disease, no disease. Anybody you bring in, I am going to classify as no disease. Okay, now what is going to be my accuracy?
Less than 50%.
No, you got the number 15, but let's get it sharpened. Please Dubey, please go ahead.
It is going to be overfitting because here every data point is going to be.
We do not know what overfitting is.
Okay. Maybe here because my accuracy is going to be very close to 100% because every point is like every data point I have
Let me
is
ask you
showing
one question.
no data. Yeah.
Okay. So you bring in one person who does not have a disease. I classify it no disease. That's fine. You bring one person who has the disease. I classify this person as no disease. Correct? This is what is happening. Look at the data and tell me for what kind of people I will make error.
I will make an error for the person who has no disease because
who has no disease, I don't make any error because I'm correctly saying no disease.
So okay, so basically, I'll put it into a different way because I know about type 1 and type 2 error. So here I'm making a type 2 error. Is that correct?
I do not know that. Let's stick to layperson language. Simply, you bring in a diseased person with a disease. I say no disease, so I made error. Correct?
False negative.
You bring a person with the disease. I say no disease. That is error. You bring a person without disease. I say no disease. That is correct. Correct? You agree? For no disease, I am saying disease. For no disease, I am saying no disease. For disease, also I am saying no disease. So I make error for all people with the disease. Correct? Yes, no?
Yeah, that's correct.
Now tell me, what is my error rate or what is my accuracy?
It'll be 0.5, right?
No, it's not 0.5.
85%.
85% accuracy.
85%, right?
Yeah.
Right, 85%, because 85%
Right.
of the population
Yeah.
did not have the disease. So
Yes.
my accuracy is also 85%.
Yes.
Okay, so is this model better than my model?
Yeah, here, this is the place where accuracy misguides us.
Exactly. Accuracy misguides us. In fact, why does it happen? This happens because one class has a small percentage of data and predominantly the data is in the other class. This is called class imbalance. Okay? If both classes have approximately equal, say 60-40, okay, then it's okay. But here it's 85-15, huge imbalance. When you have class imbalance, accuracy is a very poor marker of how we do things. So we will not look at accuracy. So what else can we do? Then we had to ask a question, okay, you got 85% accuracy, that's okay. What percentage of people with the disease you correctly identified as having disease? What percentage of people without the disease you correctly identified as not having the disease? Those are the kinds of questions we will ask, right? And that is what we are moving to in the next slides, okay? And that's called the confusion matrix, okay? That's a very sad nomenclature. It's stuck with the data science community, confusion matrix. In the psychology and other domains, specifically psychology and the math people, they call this truth table, okay? Truth table. But confusion matrix, that's a very attractive name. So we will rename that. So what is confusion matrix? Confusion matrix is, we draw this 2 by 2 matrix where we say how many of actual class 0 we correctly identified as class 0, how many of class 1 we correctly identified class 1, and vice versa. Okay? This is the output from Python. We usually don't give it this way. We actually give it the other way. We usually write the class 1, the one in the above, top layer, bottom layer. Success, failure, 1, 0. We usually write like that. But this one gives 0, 1, Python. So that's why I put it this way. But let's look at the one on the right hand side. That's what we are looking at. Okay. So only few people, only 15% got the disease, right? In the training set, okay, out of all the people who got the disease, okay, only 18 were correctly predicted to be having the disease. 367 out of all the people who had the disease were classified as not having the disease. Okay, so you see, we are missing a lot of people who had the disease. Maybe total cholesterol is required. Okay, maybe I should take back my statement. And look at this. This is very good. Why? People not having the disease, a lot of them were correctly classified as not having the disease. Only very few, only 16 out of 2,175 people, out of that, only 65 were classified as having disease. So this model is able to correctly identify class 0, but not class 1. And this is again a problem of class imbalance. This is again a problem of class imbalance. We have to deal with it somehow. Okay, that's for another day. But remember this. Okay, so we have this same thing. You could observe the same thing in the test set also. Okay, very good performance in the people who did not have the disease. Actually, they did not have the disease. How many? 926. Out of these 926, only 8 were classified as having the disease. Whereas in people who actually had the disease, only out of 172 people, only 15 were correctly identified. Right? Only 15 were correctly identified. So you see, the performance is now, even the performance is not equal in the two classes. It's very different. So we need to have matrices for actual class 1, for actual class 0, predicted class 1, predicted class 0, something like that. We need to have matrices that capture these things. And that is where these terms come in. What are these terms? Accuracy, which we know. Okay, before that, okay, let me do one simple thing. I hate this when this appears out of no place. Okay, Control Shift. So this is the truth table structure. We are getting very close to our usual end time. I'm not going to stop. I'm going to continue. So what I'm going to say is, if it's too late at your place, please, you are free to, anyone, if you want to, you can drop off from the class. But I'm going to continue and go for another half hour. Of course, the recording will be available to you. You could come back and watch this later. Okay, but if you can stay for another half an hour, we will finish this particular segment, namely logistic regression. Classification will finish today. Okay, so this is the structure of the matrix, confusion matrix. What is it? The actual class 1 are positive, actual class 0 are negative, predicted positive, predicted negative. Okay, and we have these matrices named, the cells are named like this: true positives, true negatives, false negatives, etc. Okay, what is it? True positive. That is, prediction is positive and it is true. That's what it means. This is a characterization of the prediction. What does it mean? The prediction is positive and it is true. That means actually also it is positive. You look here, it's false positive. Prediction is positive, but it is false. That means actually it was negative. That's what it means. Mohammed, yes, please go ahead.
Professor, though we use confusion matrix, we have to resolve the bias in the data with stratified sampling or oversampling or undersampling. Is that correct?
Yes, that's a technique used. So what Mohammed Niaz is saying is, there is imbalance in the data, right? So we need to somehow make the data balanced. So what we can do is, this is the technique. It's a simple technique. I more than oversampling, I like undersampling in these kind of situations and doing multiple runs. So what I will do is, I will segregate the data into these two sets, okay, namely class A, class B. If class B is smaller, let's say 15% of the entire data is class B, then I will randomly select 15% from class A and the entire class B, put them together, split it into training and test, create the test. Or you create the training set, take 15% of class A and the entire class B, do one model. Put them all back, randomly another 15% of class A, this entire class B, do another model, do a lot of these models, okay, lot of these models, okay, and out of these, okay, what you would get is you would get the parameters start appearing closer and closer in certain situations, okay? And you group them together and maybe take a kind of an average of these parameters and do use that as your final model. Some kind of this called undersampling. There's another way you can do. You can do oversampling. Okay, what you can do? You can make this 15% to be 85%. Okay, by just repeating these numbers again and again. Okay, and then split it into training and test randomly. Do the therefore the entire set will become 50-50. Okay, so now what you do is randomly get the training set and test set, do the model, repeat this again and again because you have artificially inflated the class B. You keep doing that again and again, a lot of iterations, repetitions, and then see what model gets converged. That's called oversampling. So that's what Mohammed Niaz was talking about. Okay? So that again, as I said, for another day, or you can read about this in blogs and other resource providers. The confusion matrix, we call them true positive, false negatives, true negatives. This is a descriptor of the predictor. The predictor, what it says, it's negative. The prediction is negative and it is true. What does it mean? It means the actual value is negative. False negative. That means the prediction is negative, but the prediction is wrong. What does it mean? The actual value was positive. Okay, that's what this means. True positive, true negatives, false negatives. Okay, what do we do then? We define accuracy. We know that the true positive plus false true negatives divided by everything, sum of all these things. That's accuracy. That's a poor metric. We use something called the sensitivity. It's also called recall. Okay, in the data science world, they call it recall. I have always used it as sensitivity. How good the model is, how sensitive is the model to the actual positive values. Okay, true positive divided by the actual positive. True positive divided by the total actual positive. That's called sensitivity. So in our Framingham heart disease model, the sensitivity was very poor. Okay, sensitivity was very poor, right? It was like only 15 out of 926 or something like that, right? Very poor. How about negatives? True negatives out of all actual negatives. That is called specificity. It's called specificity. Okay, so that in our Framingham heart disease study, this was very high. Specificity was very high. Sensitivity was poor. Okay. In ideal situations, we would want sensitivity to be high as well as specificity to be high. Correct? That's what we would want. But these are not the only true metrics. Okay, sensitivity may be high, specificity may be high. But what if these two actually interact? For example, if I predict somebody to be having a disease, okay, then I ask the question, how strongly can I believe that prediction? Then what you have to do? You have to look at true positive as a proportion of predicted positive. If this number is close to 100, okay, this proportion is close to 1, then you know your prediction of positive is reliable. Not sensitivity, but this vertical thing. That quantity is called precision. True positive divided by total predicted positive. Okay, when the prediction is class 1, okay, how reliable is that? That is given by precision. What is this sensitivity? If the actual value is positive, how many of the actual value does my test pick up? Okay, that is what sensitivity is. These two are very different, right? These two are very different. This says something. This says a complementary information. In the population, if somebody is having a disease, is my method able to capture that? Yes. How well? That's given by the sensitivity. On the other hand, I'm saying this method says somebody has a disease. How reliable is that answer? If false positive is also very high, let's say true positive is very high, false negative is small, then sensitivity is high. But true positive is high like before, but false positive is also high. If that happens, then what happens? Precision goes down. So when my method says somebody is positive, I cannot say for sure whether the person has a disease or not. Okay, let's take a simple example. That's a confirmatory test. Let's say I came up with a image analysis technique, okay, which if a person has a disease, chest X-ray, let's say, for some kind of pneumonia. So this analysis, when a person, 95% of the people who has this particular pneumonia, my method is able to capture. Okay, that means very high sensitivity. Okay, but let us say 30% of people who do not have the disease, my method says they have the disease. Okay, so sensitivity is very high, but what happens to the this precision? This becomes low. So when my algorithm says that somebody has the disease, should I go and treat this person or not for pneumonia? Right? So in certain situations, I need precision to be high. In certain situations, I need sensitivity to be high. In certain situations, I need specificity to be high. What situations? When you are going to make, very important decisions based upon very important decision for the positive category, then precision needs to be high. Why? Let's say, for example, somebody with pneumonia, and this method says pneumonia, and based upon this method, I'm going to start a treatment. The treatment is going to put this person, into financial strain because this is a very new drug, which is costly, and is going to knock him out, for a few days, very groggy, So for a few days, this person is not going to be as active as a normal person. Okay, if that is the case, then if I start this treatment for a person who this method said has the disease, but actually this person did not have a disease, what could happen? So there's no disease, nothing to cure, but all the side effects will be there. Right? So it's a drastic situation. So when you're going to make tough decisions on the positive cases, you need to have precision to be high. But let's say you are doing a screening test. If somebody has this particular disease,
doctor.
Yeah.
When you say high, how much is high in general?
There is no number I can tell you. It varies from problem to problem. It varies from
for example, the problem you just said in the example. So if it's you, what the number of high you will decide?
Again, you look at you see these numbers alone don't guide us, because what action you are going to take based upon this decision, that's what usually will guide us. Let us say if it is a cancer treatment, even pneumonia is okay, but cancer treatment, let's say if you are based upon this particular technique, you are going to start chemotherapy on somebody, and if this person doesn't have the disease, then this is disastrous, really, really disastrous. There, you would want precision to be very high, close to 100%, 98, 99%.
Okay, got it.
But if it's a seasonal flu, okay, somebody comes with a seasonal flu, there is this test. Now you have a temperature measuring device, thermometer, and it says fever, and you are giving some antipyretic, something to reduce the fever. It doesn't matter. Their precision can be small, 70%. Fine, okay.
Yes.
Right.
Understood.
So, yeah. Whenever we are doing screening is what? If somebody has a disease, I have to touch that person. I don't care, because what am I going to do? Screening is something that it's like a first filter. If somebody is caught in the screening, they will go for further tests, and there I will make the decision. Okay. So screening, we don't care about precision, we don't care about specificity. Okay, we care about sensitivity. We would say if somebody has the disease, they should be captured. If they don't have the disease, even if they are captured, don't worry, because in the next stage, we will correctly identify you and will drop you. Right? So, for example, you have for breast cancer, let us say, okay, ultrasound, okay, mammography is a tool that we do, right? But that's a screening test. What is the actual confirmatory test? You should do a biopsy. Biopsy is so the screening says that there is some deformity. Okay, so you get this person, do a biopsy. In the biopsy, you say, no, you don't have any malignancy here. Go home. Well, back go. So in screening, if having high false positive doesn't matter, but false negative should be small in screening. Sensitivity should be high. Okay, we don't care about precision or specificity. So whether we use sensitivity or precision or specificity, that depends upon the problem at hand. From the examples I discussed, you would see that sensitivity and precision, they are like pulling each other, pulling and pushing. It's like a push and pull between these two. So in many situations, especially when we are dealing with all this arbitrary data where we do not know what is happening, we need to find a good balance between sensitivity and precision, and that is given by this quantity called the F1 score. Okay? F1 score is what is called the harmonic average. Harmonic means reciprocal. Okay? Reciprocal of the F1 score is the average of the reciprocal of recall and precision. Okay? So that's called the F1 score. So in data science, you would see that many a time in classification problems, blindly people will give F1 score, and based upon the F1 score, they will see whether it's a good or not. Why? Because F1 score talks about the upper limit for the two quantities. Okay, let's say F1 score happens to be 80%. Okay, then recall can be up to 80%, precision can be up to 80%. Okay, well and good. If F1 score itself is 60%, 0.6, then recall can be only up to 60 and precision can also be only up to 60.6, right? So in a sense, if we know F1 score, we already know how much recall or precision can go, how high they can go. Okay, so having these ideas, when we go and calculate all this, so which one do we use in our Framingham heart disease study? Okay, this we are going to say, are we going to treat it like a sensitivity tool that is a screening device, or are we going to treat it like okay, I'm going to negate people. I'm happy as long as I say that this person does not have accurately, if I identify people who do not have the disease. That we are not going to say. We are going to say either I'm accurately identify people who have the disease. That's what we're going to say. So we should look at the sensitivity for the Framingham heart disease study. Of course, remember, sensitivity is very poor, specificity very high, right? We saw that. Look at the precision, it's only 50 or 60%. And look at the F1 score, okay, it's only 8 or 15%. Okay, so you would see that this particular this particular model is actually not doing that great job, because sensitivity or recall, which we actually want, is very, very poor in this situation. Okay, another few more minutes. Spam filtering. Here is another example. Spam filtering. Okay, some numbers. Let's not worry about these numbers. I calculate sensitivity, recalls, or precision, specificity, accuracy. Some numbers. I don't even care. Okay, some numbers. So recall is poor, precision is fairly okay, accuracy is okay, specificity is fantastic. What does it say? If it is not spam, it correctly identifies as not spam. 95%. That's what you want here. Right? In a spam filter, you want, if you say something is not spam, okay, sorry, if something is not spam, you should be able to correctly identify it as not spam. That is specificity. That is good in this case. Is that enough? Is that enough in this situation? Okay. In this situation, this is not enough. Why? Now, we give this very funny, simplistic example. Okay, let us say your spam filter, it works on multiple things. But let us say this spam filter also uses this information, namely the presence of the word free means that the mail is spam. It has somehow learned that. It has learned a lot of this going through this during the training phase. Whichever mail was categorized as spam, a lot of them had the word free in them. So it has learned that the appearance of the word free means it's spam. Now, there is this office where there's a message from the CEO, take the case of back to office mandate. in this situation, there's a message from the CEO's office saying that there is a meeting, very important meeting for all the heads of departments at 4 o'clock on Friday evening. Okay, and then following the meeting, there will be free cookie and coffee. The same. So what happens? The the spam filter sees the word free, puts it in spam folder. None of the department heads saw the saw the email, so nobody came to the meeting. Okay, so if this is the situation, okay, that's a very dangerous situation, right? So there are certain situations like this where you want specificity to be high, but precision also you want to be high. Why? When it has said spam, it better be spam. In this case, a non-spam has been categorized as spam, which is a dangerous thing. So there are certain situations where specificity should be high as well as precision should be high. What situations? Only the problem will define that. Only the problem will define that. Okay. Remember, these things do not come from these numbers 952, 526, 167, 3025. They do not come from the model. They come from the model followed by our decision criteria. Okay, drawing the boundary. Okay, threshold for probability. That's what defines these things. Now, therefore, we have to ask the question: how do we identify that boundary? How do we identify that boundary? Okay. And for that, we are going to take a small detour. This idea is called receiver operating characteristics, ROC curves. Some of you might have heard that. Okay. I do not know if this picture is clear in transmission to your laptops, but what it is you can see there are 3 people sitting in the bottom here. They are looking at some monitors, and there are these big screens here. Okay, looks like there is the reflection of a person pointing out to something here. I do not know what this is. What these people are doing is they are looking at radar screens. What is radar? So it's essentially, it emits a radiation and then hits an obstacle, gets bounced back. So from the time of travel, from when it was sent, radiation, this pulse was sent and then it received. Between the time difference, by using the time difference, we could accurately calculate how far away was the reflecting object. If the reflecting object is moving, what happens is the radiation that we sent, it has some frequency. Because that object was moving, it gets reflected from there. The reflected radiation will have a small change in the frequency. That's called Doppler effect. So we measure the Doppler effect also. That way we can see which direction it was flying and how fast it was flying. And this is a very useful tool, of course, in identifying flying objects, right? So radar, just. But the point is, during the Second World War time, they were trying to solve this problem, namely, when a blip appears on the screen, is that blip corresponding to an actual aircraft, or is it a flock of birds? Or is it a flock of birds? That was a question they were trying to solve. Okay. That is, it is an aircraft or not. Can be a flying flock of birds, or it could be anything else. All they wanted to know is whether it's a flying aircraft or not. Okay, so it's a binary classification. So what do these people do? These people, of course, these were all many of them are actually physicists. Okay, and they came up with a very interesting idea, namely, let us think about these 2 categories. Right, one category which is the flying aircrafts and everything else. Okay, everything else. We will assume that in our data, everything else falls in a normal distribution, and the aircrafts, they also fall in a similar or identical normal distribution. The only difference between these 2 normal distributions is that separation. Okay. Now, if this is the case, okay, now they ask the question: all the class 0 has this blue distribution, all the class 1 has this red distribution. Okay. This distribution, okay, comes from your prediction. This comes from the prediction, let us say, not from the data, from the prediction. Okay, that's what it has done. From the prediction data, this is what we have. Now, if the separation between these two Gaussians is high, that means our data, our model is able to separate the two classes very good. Okay, so very good. If it's very close by, then the separation, the discriminability of the model is poor. We call it the discriminability of the model poor. That's okay. But then these two Gaussians does not tell us classification. The classification is something we do. This black line that's here, that's what we do. We put the threshold here. Okay, so if this is the threshold, okay, then let's look at these two graphs. If you look to the right of it, we have this red curve, everything in the red curve. Okay, that is the true positive. The part of the blue curve to the right of this threshold line, that is the false positive. Okay, true positive, false positive. Correct? True positive is here, false positive is here. Likewise, if you look in this to the left hand side, all the blue, the entire blue is the true negative. The part of the red is false negative. Okay. Now let's ask a very simple question. Let's see what happens. Okay. Instead of let me do one thing. Okay, I cannot do that. It's a simple. Okay. So initially, this is what the threshold I have. So this is what it is here, right? When I move this threshold to the right, okay, that is I increase the probability to be higher. What happens to true positives? True positives decreases. What happens to false positives? False positives also decreases. Right? Both positives decrease. Look at negatives, both negatives increase. False negative increases, true negative increases. Right? Technically, what we would want, we want false positive to increase, true positive to increase, false negative to decrease. Ideally, that's what we would want. But look at this, this clearly tells you that that cannot happen. That cannot happen. Right? That cannot happen. So if you change the threshold, true positive as well as false positive both increase together or decrease together. What does that mean? Let's look at the data and understand. Okay, so here the same data set for the Framingham heart disease study from the same data set. Okay, so true positives, false positives, true negatives, false negatives. Okay, I start with a probability value of 0.9, very high probability, no, close to 1. That's why I've said the threshold. True positives, false positives are zeros. True negatives and false negatives are these numbers, 922 and 170. Very good. So as I decrease the threshold, that is from the right, I'm moving towards the left, that threshold line, that line, the two Gaussians, and I'm going this way. Okay. So what happens? True positive and false positive both increase. As I decrease the probability, you see true positive and false positive, both of them are increasing. When they are increasing, true negatives and false negatives, both are decreasing. Both are decreasing. See that? This is very important. Very important. So they made this observation. So this is without CHD, this is with CHD. Okay. So they made this observation, and then let's convert them into proportions. True positive rate, false positive rate, true negative rate, false negative rate. That is, divide true positives by 170. True positives by how much? 140 plus 468. Okay, true positives. 170, and true negatives by 922. Do that. Do those fractions. Okay, do those fractions. Then you will get true positive rate, true negative rate. What is true positive rate? True positive divided by true positives plus false positives. Right? That is your true positive rate. That is our sensitivity. True positive rate. What is true negative rate? That is specificity. Right? Now, what they asked us, okay, do the true positive and the false positive, do they increase together? How do they increase together or decrease together? Can we measure, can we get a study on that? Okay. If you look in this data, you can clearly see false positive rate is nothing but 1 minus true negative rate. Check that. 922 by 922, 1 minus this is this. 1 minus 921 by 92 is 1 over 922, so on and so forth, right? So this quantity is called 1 minus specificity. These engineers, what they did was, they looked at these two quantities, that is sensitivity and 1 minus specificity, not specificity, 1 minus specificity. That is true positive rate and false positive rate. That's what they are looking at. Okay, this table is called the ROC curve, receiver operating characteristic curve. Once you know these two, you can calculate these other two. Okay, so you just need to know two of these columns. That's all. Okay, so but they chose this. This is what they use. So they call it receiver operating characteristic curve. Okay, so this table, when plotted with 1 minus specificity on the x-axis and sensitivity on the y-axis. Sensitivity on the y-axis, 1 minus specificity on the x-axis. When you draw that, this is the curve that we get. This is called the ROC curve. It's called the ROC curve. Let's take a look at this curve. 5 more minutes, we'll probably finish this. Remember, these are proportions, or these are probabilities, right? True positive rate, false positive rate. Therefore, these numbers go between 0 and 1. So the x-axis goes from 0 to 1. The y-axis goes from 0 to 1. Therefore, the entire plotting area is in a 1 by 1. This is not a square. It's drawn as a rectangle, but it's a 1 by 1 square. Okay? So the entire plotting area has an area of 1, because 1 on the x-axis, 1 on the y-axis, 1 times 1 is, that's the area of the square. Right? This entire plotting area has an area of 1. Now, if you look at the curve, ROC curve, the area under the curve is always less than or equal to 1. It's always less than 1. No, only in extremely ideal situation, it could be 1, but it's always less than 1. That's a very important understanding. Now, how do we know whether it's a good ROC or bad ROC? And this is what it is. In an ideal situation, we want true positive to be very high, practically 1, and false positive to be 0. Right? So we want a curve that's rises sharp and then is flat all along. So a curve that's like the yellow here is excellent. Something like this purple here is okay. But if it's random, if the classification is random, we would get something like this diagonal line. This diagonal line. Right? So here's the thing. The area under the curve for all meaningful ROC curves will always lie between 1 and 0.5. Why 0.5? The diagonal, if you consider this diagonal, the area under the diagonal is 0.5, because this diagonal splits this square into 2 equal parts. So this is 0.5, this is 0.5. So the area under this curve is 0.5. Therefore, the ROC curve always has an area between 1 and 0.5. Okay? So close to 1 is very good. Close to 0.5 is very bad. You have to go back and look at something else. You have to look at the model. Okay? So this tells you, this area under the curve tells you how good your model is. How good your model. It does not say about the threshold. It tells you about the model. How good the model is. That's what this ROC curve tells you. Why? Because we change the threshold. We change the threshold throughout and then get this curve. Right? So it's talking something about the model. Okay? So area under the curve talks about the model. Okay? So here is a rule of thumb. Okay. Okay. If it's less than 0.5, then probably you have mixed up. You have probably mixed up the two classes. That's highly possible. Okay, that's what happens many a time. For our Framingham heart disease study, the model that we had, the area under the curve happens to be 0.732, 0.73, somewhere in the fair category, close to the poor, 0.73. Okay, on the lower end of the fair. So there is scope for us to improve this model. Okay, so we got something about the model. The main question now is, how do we classify? So what is the threshold that we should use? What is the threshold that we should use? Right, that's a question. This curve is obtained by changing the threshold. Somewhere on this curve is the optimal threshold. How do you find that? We find that by drawing this diagonal, okay, and see where this diagonal cuts our ROC curve. Okay, what is the probability threshold corresponding to that point? You find that in our case, this probability threshold looks like 0.62 or something like that. Okay, so use that probability threshold as the optimal, as a threshold for classification. Whenever the probability is greater than this number, then you classify this point as class 1, otherwise as class 0. Okay, so this is how we fix the classification scheme. Okay, so ROC curve, it's by itself sometimes it might not be great. Okay, of course, because the classification of good, bad, ugly, that's subjective. Okay, but when you have multiple models, this area under the curve is a guideline to choosing the best model. Okay. So with this, we'll stop here. So classification, binary classification is always a two-step process where you build a model, come up with a criterion, the probability threshold to do the actual classification. And what helps in doing the actual classification? The ROC curve. The ROC curve helps you identify the optimal classification criterion. The ROC curve also tells you by the AUC, area under the curve, that value tells you how good your model is. Okay. With this, we'll stop here. Oh my God, I'm close to now, wow, 3.5 hours. I didn't realize this. Okay, sorry, whoever is staying back, thank you for your patience. I'll stop here. You can ask questions if you have patience still. Okay.
Also, that based on the ROC AUC curve, you have chosen the threshold that is applicable for both the risk criterion, like you were giving that example, like somebody who was to go to the chemotherapy. So, like based on that, like the diagonal will change, right?
No, see, this particular thing. Okay, if you look at that, it's finding a balance between true positives and the false positives. Okay, so it's trying to actually balance between okay, when you have true positives, you can also, it doesn't talk about this, one of this. Yeah, see, what it's doing is it's trying to balance between how well are you capturing the population information as well as how well you are doing the prediction. So it is equally applicable to the situations where we are doing the screening as well as where we are doing the diagnostics. The method is equally applicable there. Both situations.
I mean, like, because we were working on a model where recognizing human presence in a fire accident scenario using the image. Now, there could be few false positives, that's okay, but no true positives should be left out. So it'll be slightly, the criterion will be skewed out, right?
See, if your model is good, okay, then it finally boils down to also seeing the area under the curve, not only the diagonal, but it also see the area under the curve.
Okay. Yeah,
so that means the model should be good.
Okay. That is equivalent to the R square of our linear.
Exactly.
Thanks, Professor. That's great.
Sure. That's a very interesting question. In fact, this is a kind of